Products and structures for metals are made from so-called semi-finished parts like sheets, plates, blocks, etc. A manufacturing company receives those semi-finished parts and transforms them into parts, components or products. Parts and components are elements to join with other ones into structures. Products can be the end result in itself. When talking about metals, there are three major manufacturing categories I would like to discuss: casting, machining and forming. Each of these categories will be explained briefly, and each category is based on a typical material property. The first category consists of the casting processes. The related property here is that a metal alloy can be molten. By increasing the temperature above its melting temperature, the metal becomes a liquid that can be poured into a die cavity, as shown on the left-hand side of this slide. The cavity has a number of features to facilitate the process: a runner to pour the metal in the cavity, a riser that indicates when the cavity is filled, a gate that ensures a laminar flow of the molten metal into the cavity, and a core used to create a hollow product. Other features to mention are the draft angles, the slanted sides, to ease the removal of the part once it has become solid. In this figure, the die is made of sand and can be used for only one casting. For every new casting, a new sand die has to be made. Other casting processes may have permanent dies and more complex geometries. An example of a much more complex casting is the motor block on the right-hand side. After pouring the metal in the die, the metal has to cool down, so the part can be retrieved from the die. Note that shrinkage of the part should be compensated in the die design. The second category is machining processes. Machining processes are based on the removal of material from the solid semi-finished product. This can be done by chip removing processes illustrated on this slide, or by shearing processes that will be shown on the next slide. Usually machining processes are performed at room temperature. With chip removing processes, chips or tiny bits of material are cut from the block, plate or sheet. This chipping is based on plastic deformation. Actually, the material is pushed away by high local forces. The plastic deformation and the high forces generate heat and tool wear. Therefore, processes like milling and drilling apply cutting fluids, which purpose it is to reduce the temperature, to reduce the wear by lubrication and to remove the chips. Chip removing processes can be very accurate and make very complex products. About tolerances. There are several types of tolerances as listed on this slide: form or shape control, flatness of surfaces, positioning of details, and angles between intersecting surfaces or parallel surfaces. The second type of machining processes doesn't remove chips but separates sections of a semi-finished part. Think about paper cutting using a pair of scissors. The scissor separates the useful part from the part that will not be used. The same is true for cutting of metal sheets, as is illustrated in the figure on the right. Again, the plastic deformation is the main principle. First, the force indents the material, but when the stress becomes too high, the material fails in a controlled way. As for paper, the point of shearing travels along the cutting line. A variation of this cutting is punching, where the cutting operation is performed with closed loop cutting lines. The third category is the forming processes. I distinguish here between bulk forming processes like extrusion, forging and rolling, and sheet forming processes like bending and drawing. For bulk forming processes, the material is usually processed at elevated temperatures. This reduces the yield stress and therefore the required forces, and increases the failure strain, so more complex shapes can be made in one go. These elevated temperatures are not as high as in casting processes. To give an example, aluminum alloys melt at about 600–650 degrees Celsius. Extrusion of aluminum alloy takes place between 350 and 500 degrees Celsius, depending on the alloy and the extrusion shape. Sheet metal forming, on the other hand, usually takes place at room temperature. Since the thickness is small, a few millimeters, the required forces are reasonable. By bending and press forming you can get very complex shapes. On the right hand side you see a few car body components made by press forming. Such parts are often made in match die forming processes. These processes have two matching product specific dies. For cars this is common, since the production numbers are huge, in the order of millions. For aerospace we should look for more universal processes, where processes and dies can be used for more different product shapes. Typical processes here are rubber forming and press brake bending. Sheet forming processes also encounter spring back. This is due to the elastic deformation of the metal sheet. To be able to deform the sheet plastically, we have to go through the elastic part of the stress-strain curve, or we have to increase the stress beyond the yield stress. In doing so, we accumulate elastic energy in the sheet, which gets out in two ways: spring back and/or residual stresses. The spring back part causes shape changes, like the changes in bend angles, for example, as illustrated in the lower picture. To have the right geometry after forming, we need to compensate for spring back in our die or mold design. When the part is formed, often a trimming or finishing process will bring the part to its final dimensions. For this purpose we can use the machining processes we have discussed before.